Okay, now we are going to work on part E. I just went directly to part E because as a regular college student who is broke, I actually have to work. So I'm going to be working on this one just before I leave for work. This one is probably the most challenging one on my perception. Part E is asking, what is the minimum speed Susie must have to catch up with the bus? And the keyword in here is minimum, is because we want to find like what is the slowest that Susie can go and still catch the bus. But there is an oxymoron. We still want to know what is her slowest top speed. So I know that minimum and top are kind of like opposite, but it makes sense because, for example, before when her velocity was 4.7, Susie could have got like a Red Bull and she got wins and she was able to run super fast. Now maybe she skipped breakfast like most of us and she's not running as fast as she could, but she still needs to be running fast enough to catch the bus. So one of the things that we can kind of imply here is that we know that we can kind of have to account for acceleration being equal to 0. And we need an expression in which we are able to find Susie's initial speed. So I am going to resort to our original equation in which we were comparing Susie's final position with the bus final positions. Why is this important? Because Susie's speed still needs to be dependent on the bus because the bus is moving. So we always have to have that in our equation. The bus information needs to be part of the process basically. So at this moment we know that Susie, and I'm going to use in subscripts because it will help us keep track of our work here. It's going to be very handy. Now we are going to be saying that Susie's final position is given by Susie's initial velocity times time, and we know that we learned up there in the other exercises that the bus final position is its initial position plus 1/2 its acceleration times t squared. And what we're going to do is that basically we're going to solve for Susie's initial velocity. And we have that the bus's initial position plus 1/2 its acceleration times square divided by time is going to give us Susie's velocity in terms of time. So here time is the variable. So let's go ahead and replace some values here. So, and let's also distribute these. If we want, we can have that the initial position of the bus, let me make this clear that this is a subscript, divided by time, plus 1/2 the acceleration of the bus divided by time, by time, which is equal to t, is Susie's initial velocity. So let's substitute some values. We have 40.4 meters, and I'm going to go ahead and move this t up here so we can have a more linear, cleaner, easier to handle equation. 40.4 meters times time to the -1 plus 1/2 0.171 meters per second square times time. And remember that I mentioned that we want this acceleration to be 0. So what we're going to do is that we're going to transform this equation into an equation that gives us acceleration. And what is velocity but acceleration when it's derived for the first time? So Susie's initial speed, its derivative is Susie's acceleration. And because she's at her top speed, we know that this is going to be 0. We want it to be 0 meters per second square. So we put 0 here, and we're going to take the derivative of this baby right here. So we have -1 times 40.4 meters times time to the -2. We subtract 1 here, plus 1/2 0.171 meters per second square. T disappears. And all that we do right now is -40.4 meters over time square. We just move it down. 1/2 0.171 meters per second square. And I'm not going to solve this for t using quadratic formula or moving around. I'm just going to make my life easier, and I'm going to just put it on the calculator, and I get this graph. Very nice. And the intersection of this graph with the x-axis is at x equal 21.7. Let's keep it to 3 significant figures. So at time equal 21.7 seconds, Susie is going to be at her top, let's say minimum top speed, that it will still allow her to basically catch the bus. So what we're saying is that there is going to be 21.7 seconds that will elapse, and she will still be able to make it to the bus. And to find what that velocity is, well, we're just going to go and graph this nice equation that we have here, and we're going to substitute for 21.7 seconds. So it will be 40.4 meters over, because we can move this back down, 21.7 seconds plus 1/2 0.171 meters per second square times 21.7 seconds. The good thing is that here we cancel this and we get meters per second. Meters per second, velocity is meters per second, so we already know that we're heading on the right track. And my calculator gives me the awesomest power to be able to solve this without much, by just going ahead and putting this on a table. I'm going to put our equation on a table so I can easily solve that without having to do too much math. Let the computer work. That's why we created them, so we could have more time to have fun instead of being solving problems. Okay. So I'm going to show you a screenshot. When I go ahead and put this on my calculator, I put the equation and I just put that my input value is 21.7. At that point, the velocity, which is the y value, is 3.72 if we keep it to 3 significant figures. So 3.72 meters per second is Susie's minimum top speed that she needs to be able to catch the bus. So she can skip breakfast, run at this speed, and still make it on time. And that is it for this part of the problem. Later on you're going to be asked for some other things, such as, let me center this window so you can see. You're going to be asked, for example, for what time does she have to run in that case. We already solved that. Is the result of finding that intersection of the graph of the derivative. And for what distance does she have to run in that case? Well, we just substitute time or velocity on the other equations that we have to get to this point, very similar to the way that we got the answer for this one. So you can watch part V and just go ahead and do the same procedure, just changing the input values. That's it. Let me know if you need anything through Facebook. Have a great day.